So in today's lecture, we're going to talk about partial discharges. We have discussed partial discharges in brief earlier, but partial discharges are so integral to the understanding of high voltage insulation that we will spend some more time on this. So what are partial discharges? As we have defined earlier, partial discharges refer to the partial breakdown of the insulating material only in regions of high localized electric stress. So if you consider the situation where we have a needle plate electrode, the needle has high voltage and the plate electrode is at ground potential. Let us imagine that this entire space is filled up with some gas, let's say air, and when you apply a voltage on the needle, this would be what the field looks like. We have obtained this using COMSOL. This is what the field would look like. So as you can see, the field is pretty uniform in most of the region. Most of the air sees a low value of the field. So the blue region corresponds to the lowest values. A low value of the electric field, low magnitude of the electric field, as well as the field is quite uniform. So most of the air in this entire volume does not have a problem and is able to withstand breakdown. Let's say we are seeing a situation where the blue region corresponds to 10 kV per centimeter. Air will break down at 30 kV per centimeter, so most of the air is safe. However, if you come to this electrode gap, the field is somewhat higher, but still not too high. So even here, if it is, let's say 15 or 20 kV per centimeter, we are still within the safe limit and no breakdown happens. However, it might so happen that you have, as you can see right ahead of the needle, there is considerable stress enhancement. There is stress enhancement in the yellow region and the highest stresses are available in the red region. And it may so happen that even though you have 10 or 15 or low electric field stresses, in most of the air in this gap, only in the small red region, the field may be extremely high, let's say 45 kV or 60 kV per centimeter, which is well enough to, high enough to cause breakdown of the air. But that this kind of field only extends to a very small region. So this situation will not permit breakdown of the air such that electrons can flow from the needle to the gap, to the plate. So it does not allow complete breakdown and there is no complete path created between the two electrodes. However, what might happen is only the small volume of air in this red region may break down. So this is what I mean by partial breakdown. And what does it mean to say that the air in this region breaks down? Which means the air in this region undergoes ionization, collisions, and multiplication, so electron multiplication. So probably this entire region is now filled up with ions and electrons, and no neutral molecules or very little neutral molecules. And these electronic and ionic charges will circulate and cause a localized current. So this is what is meant by partial breakdown, partial discharge. Let me remind you that when partial discharges happen in the open air, we generally call it corona. So when we are talking about transmission lines, we talk about corona. But corona is also partial discharge. We talk about partial discharge more in the context of when you have small partial discharges happening inside a solid material. So there might be gas inclusions or there might be other things. So there might be small inclusions inside a solid particles or solid insulations, which where in these small regions partial discharge happens because of local field enhancement. And most of the time we are interested in, when we talk about PD, we are talking about PD happening within solids or liquids, which we can't easily see with the open eye. It's not easily visible. What are the sources of partial discharge in solids? Anything that can cause local field enhancement can be responsible for PD initiation. So this could be voids in insulation. You have a solid insulating material, high dielectric strength, dielectric breakdown strength, high permittivity. Somewhere you have a small inclusion, air inclusion or some other inclusion, and this material has a lower dielectric breakdown strength. Let's say it's gas, so it has a lower dielectric breakdown strength. So when you apply a voltage across the entire sample, the solid part remains unaffected, but only the small inclusion breaks down. Remember, when you have a low permittivity material in proximity to a high permittivity material, the low permittivity material will also be stressed more than is usual and therefore is likelier to break down. So voids in insulation can be a source for PD. You can have delamination at insulation interfaces. So where you have two insulating materials coming together, they must be well bonded. And if for any reason there is a very small infinitesimal gap between the two layers, there will be air or some other gas, and there will be high stress enhancement in that region and partial discharge will occur. Cracking or fissures in insulation, so if there are mechanical cracks or mechanical fissures, the same thing happens. Electric field enhancement with that low permittivity, low breakdown strength material inside the gap, inside the fissure, or even if you do not have air, there would be stress enhancement because of the structure of the solid material. Treeing can be another source for PD. We're going to discuss that in greater detail later. And then there can be any kinds of manufacturing defects which leads to any kind of, there might be impurities present, there might be metallic protrusions, embedded metallic particles. So any situation which results in local field enhancement can be cause for partial discharge initiation. So let us try and understand how PD develops inside voids and solid materials. So here I have two metal electrodes, and sandwiched between the two metal electrodes, I have a rectangular solid material. Inside the solid material, I have a void. For simplicity of understanding how PD develops, I have considered a rectangular void. Of course, most voids will not be rectangular, but no matter. This is just for the sake of understanding. So you have a rectangular void with a thickness D, and in series with this void, you have dielectric material D1 and dielectric material D2. So you have a total thickness of D1 plus D2, which is in series with the void of thickness D, and D1 plus D plus D2 is the total thickness of the material, and across this total thickness, you apply a voltage V. If you apply a voltage V, the voltage will be distributed, will be divided between the void and the dielectric parts, and therefore we can write V is equal to VB into D1 plus D2 divided by D epsilon dashed plus 1, where epsilon dashed is the permittivity of the void. D1 and D2, D1 is the thicknesses of the dielectric material, and D is the thickness of the void. So therefore, of course, total V is equal to VB plus VD. VD is the total voltage dropped across D1 and D2. So this is VB is the voltage that you have across the material. So naturally, if this voltage is high enough to cause an electric field inside the void, which is higher than the dielectric strength of whatever you have inside, let's say air, then this can break down, even if V is not enough to cause breakdown of the entire D1 plus D plus D2 material. Now, what will happen in this scenario? First, I will draw and I will consider an equivalent void circuit. So this is my void. I have some material in series with the void between the metallic electrodes. What we had not considered at the previous slide is there is a considerable amount of material which is in series with the void, and the voltage across that material, across that part of the material, will not be divided up with the voltage, with the void. So this can be represented as Cp. Cp is the capacitance of the void. Cv is the capacitance of the void, and Cs is the capacitance of the material in series with the void. So this material below the void plus the capacitance of the material above the void, all these two parts, all these two capacitances club together as Cs, and Cs is the capacitance which is in series with the void. Apart from that, there will be a parallel capacitance which is in parallel to this void capacitance. So we have a circuit where we have V0 voltage applied across the material. VA is the voltage which appears across the void, CV, the void capacitance being CV, CS a capacitance of the series dielectric, CP the capacitance of the parallel dielectric. Now, let us imagine that this VA reaches a situation where the voltage is high enough to cause breakdown of the void. At that moment, the void will be kind of short-circuited and the voltage across the void will fall to zero. When the void discharges, there will be some charge which will be discharged. A discharge means charge discharge. So as long as the void does not discharge, it holds a certain quantity of charge across it. If you consider rectangular electrodes, so you'll have on the dielectric plate, on the top dielectric plate or dielectric surface, you will have some positive charge, some negative charge on the bottom dielectric plate. So this is the charge which will flow, take part in the discharge that causes the void to discharge. So let us say that some amount of charge is involved in the discharge, and that charge is neutralized when discharge happens. So the voltage across the void falls to 0, and in doing that, the voltage across the void falls, and therefore the charge must be drawn from the dielectric to restore the voltage drop. So as soon as discharge happens, voltage falls to 0, and then the air within the void is self-restoring, so it will regain its dielectric property, and when it regains its dielectric property, it will be able to hold charge across it, and therefore you will need additional charge to build up that original charge. So if you had plus q charge, you will need to get some more extra plus q charge, and where will that come from? That will of course have to come from the rest of the dielectric. So charge must be drawn from the dielectric to restore the voltage drop because of discharge. How much charge will that be? That charge can be estimated as delta Q, which is equal to delta V CVCS divided by CV plus CS. Delta V is the voltage drop, the change in voltage across the void when discharge happens. So let's say a voltage V, delta V builds across the potential difference, delta V builds across the void at the instant of breakdown. This goes to 0. So you have a change of delta V, and this delta V is related to a charge delta Q. And this is the relation in terms of the series and void capacitances. Now we can see that CV by CV plus CS will be a very small quantity. The void is very small, and therefore the capacitance of the void is very small, and therefore this delta Q can be approximated as CS into delta V. So the capacitance in series with the void into the voltage drop across the void gives us an estimate of the charge that is involved in the discharge, and this quantity of charge has to be replenished at the end of discharge from the dielectric material. How much is delta V? Delta V is VB minus VR. If you remember in the previous slide, we say that VB is the potential that appears across the void. So at the instant that breakdown happens, that's why it's called VB. I've used the suffix B to indicate that the voltage across the void is equal to the voltage that is necessary for breakdown. So breakdown voltage. So VB is the voltage across the void. As soon as the voltage across the void is VB, the void discharges. The void should ideally discharge to 0 so that all charge is neutralized, but that may not happen, and even at the end of discharge you may be left with some residual charges, and therefore there might be some residual voltage VR. So therefore delta V is equal to VB minus VR. If VR is equal to 0, it is equal to VB. So therefore this is the quantity of charge which is involved in the discharge and results in a potential drop of delta V across the void, which is equal to VB minus VR. The discharge therefore would have some energy. When the charge is involved, when charge delta Q is involved in the discharge energy can be represented as delta W, which is equal to half CV delta V whole square, CV being the capacitance of the void. So this much energy is involved in the partial discharge. So when you have partial discharge, as soon as there is a partial discharge, there is a potential change across the discharging electrodes. There is a charge involved in the discharge, and the charge involved in the discharge decides what would be the discharge energy. So partial discharges are always associated with energy, and this energy is released into the surroundings. It is released into the surroundings in many forms. How do you know that PD happens? For example, when corona happens, how do you know that corona is happening? You can see it. You can see it by the glow. So therefore, light energy is emanated. Light energy will also emanate when you have PD inside a solid, only you may not be able to see it because you do not have visual access to inside the solid material. There might be light. Corona can also be heard. So there will be light emission, there will be sound emission, there will be chemical reactions, creation of decomposition gases. For example, in air you have ozone. Here you might have some other byproducts depending upon what material surrounds the void and what gas is present within the void. So this energy is released. Energy is also released in the form of electromagnetic waves. We will discuss this later, but discharge energy is involved whenever we have partial discharges. Now let us imagine, if you look at this circuit, potential across the capacitance, let us consider that to be VA. And let us also imagine that we apply a V across the sample such that the voltage across the void is equal to VA, and that is also equal to VB. What is VB? VB is the breakdown voltage of the void. The voltage that is required across the void for the void to break down is considered to be VB. Now let us apply an electric field, let us apply a voltage across the total sample such that the voltage across the void is equal to VA, where VA is equal to VB. In that case, what should we see? Initially, the voltage across the void will increase. It will follow the supply voltage. It will reach the peak voltage at the same time as the supply voltage. And let us say that this peak voltage VA is equal to VB, which means at this point the void will discharge. So the void breaks down. At the instant the void breaks down, let us imagine that it happens instantaneously and that the void discharges completely. So after breakdown, the voltage across the void is 0 and not VR. So what we see is sinusoidally the voltage across the void reaches to VA, and then instantaneously at the peak it drops to 0. Now we still have the voltage across the metal electrodes on, and that now decreases from the peak voltage to a smaller voltage. So the voltage, let us also imagine that instantaneously the void regains its dielectric property. So it is devoid of charges, but it is able to hold charges. So as the voltage across the void begins to fall from VA to 0 because it is following the supply voltage. The supply voltage across the metal electrodes is falling from the peak voltage to a 0 voltage. Similarly, the voltage across the void only begins to fall from VA to 0. That is what should happen. However, at the peak instant, the voltage on the voltage across the void is 0. So if it has to reduce, following the supply graph, what should happen is it should reduce sinusoidally from 0 to minus VA. So as we enter the second half cycle, the second quarter cycle of the sinusoidal wave of the AC voltage applied across the total specimen, the voltage across the void will start to fall from 0 to minus VA. So first it goes from 0 to VA, falls instantaneously to 0, and then follows the wave of applied voltage to go from 0 to minus VA. We have of course assumed that minus VA is also equal to minus VB, so it's symmetrical wave on the negative and the positive half cycle. So as soon as it reaches minus VB, the void is again ready to break down, only in the reverse direction. So therefore it again breaks down, and as soon as it breaks down, the voltage instantaneously goes to 0. Now the supply voltage enters into the negative cycle. So the voltage VA across the gap will also tend to follow the supply. So now the voltage will tend to fall from 0 to minus VA. The voltage across the void is also 0, so there is no problem. It just follows this curve. So it again goes from 0 to minus VA. When it goes to minus VA, it again breaks down. So there it goes instantaneously to 0. And when it enters the latter part of the negative half cycle, Instead of going from minus VA to 0, it goes from 0 to minus 0 to plus VE. So what, and again, as it reaches plus VA, it breaks down again. This is of course an ideal situation. So what happens is, as soon as discharge happens, as soon as the breakdown voltage is reached, discharge happens, voltage goes to 0, and again the voltage across the void changes. The net result is that within one cycle of the supply voltage, you see 4 partial discharges. 1, 2, 3, 4. So pulses, the partial discharges are pulsative in nature. So PD is, therefore you have pulses of PD, because as soon as you reach the discharge condition, discharge happens, and then you again have to wait for the discharge condition to build up, and again discharge happens, and this happens several times in a cycle. Let us consider a second scenario where instead of considering VA to be equal to VB, we consider VA to be equal to twice VB. That means the voltage that appears across, we have applied a voltage across the specimen such that the corresponding voltage across the void VA is twice the breakdown voltage. So what should be the scenario here? As you follow the supply voltage, the voltage across the gap begins to increase from 0 to VA. As soon as VA reaches the value VB, this is not EB, this is VB. As soon as it reaches VB, breakdown of the void happens and the void discharges. Voltage across the void becomes 0. But the supply voltage is still rising. It is still to reach its peak. And therefore, the voltage VA that should have appeared across the void, if the discharge had not happened, would have gone from VA to twice VA, would have gone from VB to twice VB. However, a discharge has happened, and therefore the breakdown, the voltage across the gap at this instant is not VB but 0. So it will go from, instead of going from VB to 2 VB, it again goes from 0 to plus VB, at which instant again breakdown happens. Similarly, voltage goes to 0. And then as the voltage reduces from peak and tries to go to 0, you have several discharges happening. So from 0, it will go to minus VP, discharge, again minus VP, discharge. So every time the potential difference reaches the breakdown voltage, a discharge happens till it comes down from peak to 0. And again in the negative half cycle, it starts going towards the peak, and in going towards the peak, there will be as many pulses as the number of times the breakdown voltage across the void is reached. So every time VB happens, a discharge happens, again VP is gained, and discharge happens. Now, if you consider these two pictures, these two plots, in this case, VA is equal to VB. That means the voltage that appears across the void due to the supply is twice the breakdown voltage of the gap, and you have 4 pulses. Here I have increased the sample voltage so that the voltage that appears across the gap is twice the breakdown voltage necessary for the gap to discharge. And in this case, you have 8 pulses. So therefore, the number of pulses that you would have in a single cycle of the supply depends upon the relation between the supply voltage peak and the breakdown voltage of the void. Generally, the void is very small compared to the sample, compared to the peak voltage, and you will not have just 2 or 4. You will have a very large number of PT pulses happening in any cycle of the supply voltage. So this is to explain that PD is pulsative in nature, and the number of pulses that you would have per half cycle, per cycle of supply voltage depends upon the relation between the breakdown voltage of the void and the voltage that would appear across the void depending upon your CV and CS. And the number of pulses would be an integral number. Now, why are we interested in PD? We are interested in PD specifically because PD monitoring is one important diagnostic tool that we use in insulation. We've just started talking about measurement techniques where we have discussed very basic measurement circuits. But remember that when we are measuring properties of insulation, we're really more interested in measuring properties without destroying the insulation. And that what we would like to do is we would like to estimate the aging condition, the lifetime, the health of the insulation without causing destruction to the insulation. And in that, in condition monitoring, PD monitoring is an important aspect. We will discuss this in greater detail later when we talk about other non-destructive techniques. But right now, when we discuss PD, we are going to talk about PD monitoring. That is, how do we use partial discharges to monitor the health of an insulation system? There are two very important aspects to PD monitoring. When partial discharges happen within an insulation, it means that something is wrong. There is a void inclusion or there is a protrusion. Something has gone wrong somewhere so that you have local field enhancements. So therefore, the occurrence of PD in an insulation is a symptom of degradation of the insulating system. So it's a symptom. Just like when you are unwell, you have fever. Fever is a symptom, but fever can be due to many causes. Fever can be because you have a simple cold, in which case you don't have to do anything. Fever can be because you have the flu and you need medicine. It can be due to COVID, in which case you have to wait and hope for the best. It can also be cancer, in which case you have to do something, but that something will be completely different from the course of action in other situations. So what I'm trying to say here is that PD is like fever. PD is an indication that something is wrong in the insulation system and that we need to take action. We need to pay attention and take action. Secondly, PD is also a stress mechanism in itself. So, for example, when you have fever, fever is a symptom that something is wrong. But fever is also a means of the body to fight your infection, which is all very well. But then if the fever rises to a very high degrees, fever goes beyond 105 degrees or so Fahrenheit. In that case, the fever itself can be detrimental. Same with partial discharges. The partial discharges gives you an indication that something is very wrong and you might need to take action before catastrophic failure occurs. But it might also be that if you have a PD, maybe something is not that wrong. It's okay. I mean, it's a problem that can be ignored. But what might happen is this PD, if it continues to happen, it is a stress mechanism. It causes stress to the surrounding insulation. And then the PD itself can become a cause for worry. It can itself drive the insulation to deterioration and ultimate degradation. So these are the two things that we have to remember. The PD can be both a cause as well as an effect. It can be a cause for deterioration or degradation. It can be an effect of degradation and maybe just a warning symbol. So it's a signal. So we need to understand what is going on and we need to take appropriate action. The stress mechanisms that are related to PD can be of various types and we are going to discuss that in the next lecture.